Today we are going to continue with our discussion on the linear optimum filter, and I'm using today to summarize the linear optimum filter and conclude with this filter design. Okay, so we are doing an optimum linear filter, and we're starting from optimum linear estimator, and you will find out these two concepts are very close. So either it's a filter or estimator. In signal processing, we also call that estimator because we want to estimate a signal. Given some input, we want to estimate what is the final output from a filter in our case. Then compare with the desired signal, and then we optimize this estimator or the estimator coefficients or the filter coefficients. Optimal in a sense that we are optimized the mean square error, the minimum mean square error method. So we want to optimize the error, of course, and then because the error going in both directions, either positive or negative, we want to minimize the square of the error, and over a period of the data collected, we want to minimize the mean of the squared error. So it's mean square error optimization. The mean square error is a function of the coefficients, and that is py subtract d commission r-1 d plus rc subtract d r-1 and then rc subtract d. Okay. So this is what we have for the mean square error, right? A few things we need to clarify. So here what we have is we got a x coming in, x1, x2, all the way to xm. And then they will be weighted by c's, c1, c2 to cm. c1, c2, cm, then they combine together. All these, they combine together and give me a y. Y is my estimation, so y hat. We want to tune those c's. Actually, it's a complex number. We're using c complex. Filtering, we always do one vector times complex conjugate of another vector if it's complex number. And what we want to find, those coefficient c's, and then make sure that this output or the estimator of y should be as close as possible to the true y. True y is that it goes through, for example, a physical filter, okay, or it goes through some process that's indicated by these c's that give me a perfect value. It's a perfect y. That's caused by some physical effect. And the error is these two, and of course we're doing a mean square error. So in this expression, now we know this py is expectation of y absolute value square if y is complex, so I'm using absolute value square. So what is that? This is the output. That should be the true output. That is independent of c, has nothing to do with those coefficient c's. And we are using the expected value. Now, x and y, they are all random variables, so expected value. So this is the first part. And then we have a r here. This r is a autocorrelation matrix, right? Now, in this case, all these random variables, they are zero mean. So that's, I have autocorrelation matrix, and it is equivalent to an autocovariance matrix because it's zero mean. If I'm solving for this optimal linear estimator or optimal linear filter, when these variables are non-zero mean, and it's very simple, you just simply subtract the mean of this, so subtract from the random variable. So we have a zero mean, and we can talking about autocorrelation matrix. So this is the expectation of x times x permission. That's the autocorrelation matrix or autocovariance matrix, again, if it's zero mean. X is a vector. X is a vector. That is x1, x2 to xm with dimension m, or dimension m times 1. So that's x. Let me using a underscore here to just indicate that this is a vector, trying to indicate this is a vector, x is a vector. So it's a vector, d is a vector, d is a vector. C is also a vector here. Okay, so that is my autocorrelation matrix. And to write this out, now, what's the dimension of autocorrelation matrix? It's m times m, right? Because x is m times 1, x commission is 1 times m. So the entire thing is indeed it's a matrix. I just write the element. So the ijth element is the expectation of xi, xj conjugate, okay, which is also equal to the jith element conjugate. So each element of my matrix. So this is autocorrelation matrix defined as R. And then we have this vector D. D is a vector of cross correlation between X and Y conjugate if Y is a complex number. So the dimension of that is m times 1. X is a vector, Y is a scalar. So we have this. And for each element di, the ith element of this vector D is equal to the expectation of xi times y conjugate. Right. So these are how we defined in this expression for mean square error. So last time we talking about the mean square error should be written in this format. And then what is the minimum mean square error estimator? So the minimum mean square error estimator which is the best coefficient, that's called C0. And that satisfies an equation. The equation is the normal equation equals to D. Okay, this is a factor. So that is the normal equation. Last time we find out this is the best what we can get. Now, where does that come from? Well, it comes from here. It comes from right here. Because this is the only part that is a function of C. And we know this is a very nice structure here. In the middle is my R to the power -1. R is a autocorrelation matrix. Autocorrelation matrix is positive definite. R is positive definite. That means when you multiply by a vector transpose times a vector, left multiplication, right multiplication, you got a number. This number is always positive. It's always positive. And when does that give you a minimum, which is a 0, is that if this vector here is a 0 vector. For any non-zero vector, it's always positive. If it's non-zero vector, if it's 0 vector, of course, this is 0. And a little tricky part here is this is R to the power -1. That's the inverse of R, but it's the same. Inverse of R is also positive definite. So we have that. So the minimum we have is then when this part is a 0 vector. That's where we will conclude here. That is the best C I can have in order to have this term in red is 0. So I get the minimum mean square error. Okay, so that is the solution. We know that the best C is calculated as R inverse, the inverse of autocorrelation matrix times D, and that's vector. That's the best we can have for the minimum mean square error estimator. Now, if we plug this in, of course, when you get this the best estimator, then this is 0. This is 0. So the third part, this goes away, right? We know at the minimum mean square error, P0, that's my mean square error but at the best point, that's my minimum mean square error, which is equal to py, same thing, that is expectation of y absolute value square, has nothing to do with c, subtract d r negative 1 d, okay, which is also py subtract d c0, right? This part is we defined, that's our c0. So that is the solution for the optimum linear estimator, and we find the using the normal equation, then we find this best estimator is in this format, and the minimum mean square error is this. So you need to remember, and this normal equation has been used a lot in optimal estimation, in optimal linear filtering, as we will see. So now we have know what is the best coefficient that we have for an arbitrary, for a arbitrary c. For arbitrary c, that a c is the best part. This is also vector, the best possible estimator in the sense of minimum mean square error, plus a deviation. This is also vector. This c tilde is the deviation. Deviation from the best solution. Right? We plug this into our mean square error equation. So mean square error equation, now we have this c is c0 plus c tilde. Again, these are vectors. Let me just, without writing the underscore, but we know that's a vector. That is py subtract d, Hermitian r negative 1 and a d. These two parts has nothing to do with c, so it's very clear that's the same. And then the third part is r c, which is c0 plus c tilde, subtract d, Hermitian r inverse, and then we have r times c, which is c0 plus c tilde, subtract d. Okay, so that is the expression for the mean square error. Now, following this, and we know we can put in together, that is the minimum mean square error, evaluate on the best c0. So we actually have r c0 subtract d, r c0 subtract d here. Then what we left here is we have r c tilde Hermitian times r negative 1 and r c tilde. So what's left here is r c tilde Hermitian times r negative 1 and then r c tilde. Okay. So that part is equal to pc0. That part is c tilde Hermitian, r Hermitian, r negative 1, r c tilde. R negative 1, r to the negative 1, which is inverse of r, times r, that's the identity matrix. So it cancels out, that's identity matrix. And we have r Hermitian here. Now R is the autocorrelation matrix, right? It's autocorrelation matrix. It's a Hermitian matrix. So it's when you do the transpose and then conjugate, it's itself. So what we said here is, this is true for the autocorrelation matrix. Therefore, this part is just simply becomes C. I'm using that. This part is C tilde H R times C tilde. All right, and this part in blue, we call that the excess mean square error. That's the error beyond the minimum mean square error, something that it is caused by the deviation or the parameters you choose. So I have some non-zero error, non-zero, which is non-zero beyond the minimum mean square error, beyond this error here. Okay. So with the concept of an excess mean square error, Last time we get into an idea called the principal component analysis. PCA stands for principal component analysis. We did some math last time. It's basically doing the a matrix singular value decomposition or Eigen decomposition if the matrix is square matrix. So for the eigenvalue decomposition for R, we have a Q lambda Q Hermitian. All right. R is a square matrix. R is autocorrelation matrix, so it's square. It's M times M. And because of the feature of this autocorrelation matrix, it is a Hermitian matrix. We know we can do that with the lambda are all real numbers. Actually, they are positive real numbers because R is positive definite. Now, if R is positive semi-definite, we have all these lambdas, they are non-negative values, non-negative real values to all the way to lambda M Q. Okay. And we know the element of R can be complex, right? Because in general, my signal X and Y, they are complex. But because of this very nice feature of a positive semi-definite matrix, so these eigenvalues in here, they are all real. They are all real, and they are all the negative. Okay. As a matter of fact, they are representing the power in the subspace of the matrix. And we will talk about this momentarily. So here is the decomposition. Now, the Q matrix is orthogonal matrix. Precisely, that's an orthonormal matrix. Q, we have all these column vector as element, Q1, Q2, all the way to Qm. These are vectors. These are vectors. It's a column vector with length m. Dimension is m times 1. It's a column vector. So you stack all these m columns together. We got this matrix called Q. For each of those vectors, Q1 Hermitian times Q1 is 1. If Q1 Hermitian times Q2, that is 0. They are orthogonal. So each column, they are orthogonal to each other. But the length of each column is 1. The length of each column. Length meaning the length of the vector, which is in this case, that is the length of the vector. I'm using the mole of Q1. In this case, it's a square. If it's 1. So the length is 1. Right. So this is in the orthonormal matrix of Q. And then we have orthonormal matrix Q Hermitian Q equal to Q Hermitian equals to the identity matrix I. Identity matrix, which is 1 in the diagonal and a 0 elsewhere. We also have, because of this, now we know Q inverse is equal to Q Hermitian, right? Why is that? Well, by definition, if this is equal to I or this is equal to I, then Q Hermitian must be equal to the inverse of Q. So we got that. This is some of the property of my orthonormal matrix Q. Because of this Eigen decomposition, now this matrix R can be decomposed as a sum. You can write this in the matrix form, or let me just write it in this form. It's a sum of lambda I times Qi Hermitian. Okay, so this is what I spread out in this matrix form. Now I have this. So each Q is a column vector. Remember, it's a column vector. Then you multiply by corresponding eigenvalues on these positions. Let's say the ith position. I is equal to the second ith position. 3 times Q2, and then Q2 Hermitian, which is a row vector. And then you multiply lambda 2. That is one element. Then adding together all mi elements, we got the final matrix, which is R. So that is why we call it decomposition. You decompose into each element in this sum. For this sum, now we have actually, if you're looking at that, we have Qi times Qi Hermitian. this term has a dimension, it's a matrix, it's dimension m times n, right? Qi times Qi Hermitian. So the dimension of that is m times n. However, the rank of this matrix from linear algebra, we know for the rank of this matrix is only 1, because it is composed by one column vector, by one vector. And so the rank of that is only 1. It's not m, it's 1. Indeed, this is one subspace of my m-dimensional space. So if I is in an m-dimensional space, meaning that I have a, let's say, 2-dimension. I'm using maybe 3-dimension, maybe. So 3-dimension, this is Q1, this is spanned by Q2, this is spanned by Q3. So for the matrix, you can think that we have, in matrix time, you generate a vector using this matrix. This matrix is a span of Q1, Q2, Q3. So the vector is in this 3-dimensional space. But here, I'm only emphasized on one dimension. In this case, is Q1. So we have one subspace of this space of dimension 3. So one sub. And if you adding another one, Q1 Hermitian plus Q2 Hermitian, then you have another subspace which is spanned by Q1 Q2, which is this area here. That's also a subspace of the 3-dimensional space. It's a 2-dimensional space out of 3-dimensional space. It's a subspace. Okay? Now for these subspaces, and each of those subspaces has a weight. The weight is the eigenvalue, lambda 1, lambda 2, all the way to lambda m. Usually when we do a singular value decomposition, we have all these lambdas, they are ordered in the reverse order from the maximum to the minimum value. So lambda 1 is the maximum value, which stands for that over this subspace, I have the maximum signal power. Right? I is all the signals combined. So most of those signals will be concentrated in dimension Q1 because the energy lambda 1 is the largest. And the least is lambda. So over this dimension, the signal does not line too much. So again, in this example, for 3-dimensional Q1, Q2, Q3, so a lot of signals will concentrate it on Q1, concentrate on Q1 and Q2, not too much on the 3rd dimension. So if the 3rd dimension, lambda 3 is very small, it's close to 0, you can picture all these signals. They are in this 3-dimensional space, but however, they are close to this 2D plane. They're close to 2D plane. There's not too much the kind of the elevation on the 3rd dimension. Okay, so that's a very nice idea for doing this eigenvalue decomposition. That is indeed what we call this principal component analysis, where this principal come from. That's according to your principal eigenvalues. Principal eigenvalues. And I need only talking about a few dominant or principal eigenvalues, because those are the subspace of the signal space that contain most of the energy. Okay. Now in some other analysis, and I just mentioned a few words about that. If you have received something with a matrix, let's say R is 10 times 10, but you know the signal, when you compose a signal due to a modulation, the signal itself has only a dimension of 3. Right? Let's say it's a linear combination of some of 3 different modulation points. So when you do the eigen decomposition like that, ideally, you should have only lambda 1, lambda 2, lambda 3. And all the rest, eigenvalues should be 0. Lambda 4 all the way to lambda 10, they should all be 0, because the signal is not going to land in those dimensions. Now, because of the noise, you will still have those smaller parts here. But that's because of the noise effect. So you have some non-zero lambdas, lambda in my example, lambda 4 to lambda 10. So that's a very good way to remove the noise, because those are the noise subspace, right? So all we need to do is I'm doing an Eigen decomposition, and then I simply neglect those smaller case. I only, if I know the rank of my signal space should be 3, so I only taking from 1 to 3. And I neglect all these smaller variables. And then those are the things that you land on to the orthogonal noise space. Okay, so that is called a principal component analysis. So let's go back to our minimum mean square estimator. We are using that. Now we look into our mean square error estimator. We got this Q. Q is, again, this is coming from the Eigen decomposition of my autocorrelation matrix R. Let me write out again here. R is equal to Q lambda Q commission, where lambda in the middle is the diagonal matrix with all the eigenvalues, and the Q is the matrix of eigenvectors. Each of those Q1, Q2, all the way to Qm, these are the eigenvectors. These are the eigenvectors. We can, using this Q matrix, Q commission times C0. We got another vector called C0 prime. What we did is rotate a vector. This is rotation. Rotation of a vector. This vector is in the space dimension of M. So Q is M by M. This is orthonormal matrix. So it's a rotated vector. Last time we see in the linear algebra, you have this vector is rotated, but because of orthonormal matrix, so the length of C0 doesn't change. What you did is you only rotate this vector in this vector space. Okay, so therefore C0 is equal to Q times C0 prime, right? This is you're putting a Q here, Q commission is identity, so we have that. So you kind of rotate back from the new vector C0 prime back to the old C0. Similarly, I can do that for vector D. I'm also doing Q, that's D. Therefore, original D is equal to Q times D prime. Now, we are doing that is because we can simplify this normal equation, solution for the normal equation. That's the normal equation we want, right? For minimum mean square error. Then I plug in this R is doing this Eigen decomposition. So it's Q lambda Q commission. That is for R times C0 equal to D. Okay. And then I can left multiply this equation by Q commission, which Q commission Q is the identity matrix, because again Q is orthonormal matrix. So we left on the left is lambda Q commission C0, because we left multiply by Q commission. So Q commission times D. Okay, so that's what we left multiply by Q commission. And then that will give us a very nice, we will have lambda. This part is C0 prime, and then the right-hand side of my equation is D prime. Now, which means lambda is a diagonal matrix. So this is a matrix multiplication, matrix multiplied by vector equal to vector. But because lambda is a diagonal matrix, so I can write it into individual expressions of multiplication, but these are all scalars. This is the ith element equal to di prime, okay, where I is equal to 1 to 3 all the way to n. Okay, so that we just kind of simplify that, decompose into m parallel equations, and that's very easy to calculate this best solution. That's C0i prime, simple division. That's di prime over lambda I. Therefore, the minimum mean square error estimator, or the minimum mean square error can be calculated as P0. We know that's Py subtract D emission C0. And in our case, is Py subtract QD prime emission Q C0 prime, which is equal to Py subtract D prime emission C0 prime, right? Why we have that? Well, because Q emission Q, again, that's canceled out. It's an orthonormal matrix, so it becomes an identity matrix. And that is my Py subtract, and all this is sum of I from 1 to m di prime emission. Now it's one element, so I'm using conjugate, times C0I prime. That's Py subtract summation of di prime square, absolute value square, over lambda I is from 1 to m. So we can do the same thing for the normal equation and the mean square error. So we expressed that into a scalar form, it's parallel scalar form. We calculate that, and then the last one, this is my mean square error. It's very easy to calculate. Now, at this time, all we need to do is we find the eigenvalues of my autocorrelation matrix, lambdas, and then the cross correlation, which is the D, the vector D, you do a rotation from D to D prime, and then you take each element of D prime, which is the Di prime, and then we are using this blue box to find the optimum coefficients. To look that using the pictures we kind of mentioned last time, we take pictures looking to the excess mean square error. Excess mean square error is C tilde emission R C tilde. We also do Eigen Decomposition, Eigenvalue Decomposition for R, that is Q lambda Q emission C tilde, right? And then we do a rotation on my vector C tilde. So C tilde rotation is, let me call this V tilde, is we rotate C tilde using that. Therefore, we plug this into my excess mean square error equation, and this will becomes V tilde emission times lambda times V tilde. Okay, and then here, this is this very simple format because lambda is a diagonal matrix, so we can decompose that into the sum of all these scalar terms. I equal to 1 to m lambda I, and then V I tilde absolute value square. So that's the way we calculate excess mean square error. Now, using the picture we started last time, that let me do it here. Let's say I have only C1 and C2. I got only those two coefficients. So it's in the coefficient that's a two-dimensional space, that which is a plane. And here is my C, an arbitrary C, a vector C in the two-dimensional space. That's composed of C1, C2. Then I have the best solution, which is C0. That's the minimum mean square solution, optimal solution. The difference between these two is pointing to C. This is the vector, which is C subtract C0. This is the vector here. Okay, so we have this vector, which is our C tilde excess, which is different here. You plug in, that's the in the excess mean square error. So that's the C tilde. First, we do this, doing transfer to origin from 0 to C0. And then we doing a, so we got, here is my Q1 and Q2. So those are the two vectors of my Eigen decomposition, right? Q1, Q2, dimension 2. So I only have Q1, Q2. So those two directions, Q itself is just a base because the length is 1, so it's a base, Q1, Q2. And then we have this, this excess, this is C tilde. In my case, C tilde exactly land in the subspace of Q1. So very nice. I only have land. This is a dominant, and then I don't have anything. It's orthogonal to Q2. But in general, I have those two. And then this effect, you mapped. So let me just do a little bit. Let's see, C tilde is a little bit off. So I project onto Q1 and Q2. Now this part is what I have here is the V1 tilde and a V2 tilde. Then the length of V1 tilde, V2 tilde multiplied by this eigenvalue, which is how dominant is this subspace. So it says eigenvalue λ1 and λ2. And then you add in those two. These are the contributions, if you like. That's a contribution of this excess C, which is C tilde. And that will contribute to the error that you have. So this is a 2D. Last time we know the error, the excess is really the error surface. So you're kind of thinking that you're watching top down. So all these, and then the error is, if it's 3D, you got this error surface here, which is a bowl shape, and the minimum is at C0. But if you have any of C, so you have, this is 3D, so you got some errors, non-zero errors here. Okay. So basically, if it's 2D, we're looking at a contour on this 2D space. We're using this to see one of the principles, which is called a principle of orthogonality. Principle of orthogonality. Principle of orthogonality is saying that the expectation of x times E0 conjugate is, this is my expectation of the signal vector times the error. So the expectation of x, the error is y, it's a conjugate. So it should be y subtract C0 x, right? But because we're doing conjugate, so y conjugate subtract x commission C0. So we are doing, you're putting a conjugate here. So you exchange those orders of those vectors and then put a conjugate here. So that's the second part, which is here is my error, E, and then doing a conjugate. We have expectation of x times y conjugate, subtract expectation of x times x commission, and then C0, the second part. Now the first part, this part is D, right? We define D. This is what we define D. What about the second part? Well, E x commission is the covariance matrix. That's R times C0. C0 is a constant, so we can bring that out of expectation. So that's C0. And because C0, that's your best solution, that's a minimum mean square error solution. Therefore, this satisfying the normal equation, we got this equal to 0. Okay. So we have that, the expectation for each element, xi times E0 transpose, this is equal to 0. If equal to 1, 2, all the way to n. So that's the orthogonality part. That means the estimation error is orthogonal to the data. If I have the best choice, if I'm putting at the optimum linear estimator here. So the error, estimation error, should be orthogonal to data which is x, data x. That's when I have this, the minimum square error. Now let me roughly design. If I have two random variables, they are orthogonal to random variables. They are orthogonal. We have x, y, those two random variables. They are orthogonal, meaning that the inner product, all we defined here is x times y conjugate expectation, that is 0. Okay. Then for the estimation is C1 conjugate x1 times C2 conjugate x2 plus Cm conjugate xm. Okay, so if I'm thinking that I have a space is roughly defined by all these random variables, it's a linear. This is a linear combination. So each random variables is one of the directions. Roughly speaking, we can think that this is a vector lies in a subspace defined by all these random variables x1, x2, all the way to xm. Okay, so in a picture, let me draw a picture. Let's say I have a two-dimensional picture of x1 and x2. It's kind of we're doing an analogy. x1 and x2, these are really random variables. They are orthogonal random variables in a Hilbert space. But I'm using a vector in one-dimensional vector x1 and x2. So just help us to picture this. And then this combination of these two, which is here, this vector is y hat. It's a linear combination with this is C1, C2 here. When you multiply by that, you putting a conjugate here. So we have y hat is the estimation. Now the true y can be somewhere here. This is the true y. What is the error? Well, the error is between this and this. This is the error vector. This is the error vector. That's the E equals to y subtract y hat. Now that makes sense because y hat, using the minimum mean square error estimator, we will see this y hat is equal to y0. So this is y subtract y0. Okay. What we want to do is I want to minimize the error. Now, what is the minimum error you can have when this E is orthogonal to this plane spanned by x1 and x2, right? That's if it's orthogonal, then the distance is the minimum distance. Well, why do we have distance? Well, because y is true y. Y hat is the representation that using a specific, the input, you sample those input, x1, x2, xm. So we think that as a linear combination of these two, of these the inputs. So the estimation is something you can get. That's the best you can get. You will not be jumped out of this subspace. You will be here. It's different from the truth, but I want to minimize this error. The minimum error is when this distance between these two vectors are orthogonal to the space spanned by all these x. And that's what we have here. That's the principle of orthogonality. That means that this is true, which means this estimation error should be orthogonal to data. And in my case, is the subspace spanned by all these data. So it's a very nice principle of orthogonality to explain how we calculate the minimum mean square error.